Welcome back. In the second part of this section, we're just going to do a couple more examples. First one involves me creating another box, except this time I have something involving cost that I'll need to think about. I want this box to have a square base and have a volume of 2,000 centimeters cubed. And then for the sides and for the top and bottom, I'm going to use different materials that have different costs per area. One of them costs 25 cents per square centimeter. Some of the sides will use 75 cents per square centimeter material. And so the question is, how can we reduce our costs? What is the minimum cost for this box? And what are the dimensions of that box? So I guess first things first, I'm going to draw myself a little box with a square base. And if it's a square base, then the side lengths of the base are the same, x and x. And I guess the height for my box, I'll say it's h. So for this box, as I currently have it, the top, the area for it is x times x. Same thing with the bottom. It's also x times x for its area. And then for the four sides, each side has an area of x times h, and there's four of them, so 4xh for the four sides. So if we're thinking in terms of creating a cost function now, because I want to minimize a cost for this box, I'll have the cost for the top, the cost for the bottom, and the cost for the four sides. It says for the base, so for the bottom and for the four sides, I'm going to use the 25 cent per centimeter squared material. So for the bottom, the x squared, I'll use the 25 cent material, so the cost times the area. Same thing for the four sides, it's also the 25 cent material, so cost times the area for the four sides. And then for the top, it says I'm going to use a more expensive material. It costs 75 cents per centimeter squared. So for the top, 75 cents times the top area. And I kind of got a little ahead of myself when I said this is cost as a function of x, because currently it's not. Really, it's just cost, but it's not as a function of x yet, because you'll notice there's also height worked into this as well. If I clean that up, though, it actually doesn't look too terribly bad. I've got cost is x squared plus x times h. Now, the only problem is we need this to be a little bit cleaned up for us so that it's now a function in terms of just x's or in terms of just h, whichever you prefer. Probably easier to get it in terms of x's. And for this, I'm going to use the one thing that we haven't used yet, which is that our volume needs to be 2,000 centimeters cubed. So on the side, I'll say to myself, well, I know the volume is 2,000 centimeters cubed, and the volume of this box is x times h. So x squared times h is 2,000. Or in other words, h can be replaced with 2,000 divided by x squared. So that's going to allow me to come up with a cost equation that's a cost function just in terms of x. If I replace my h with 2,000 over x squared, then I now have my cost function is just x squared plus 2,000 over x. Okay, so we also have to think a little bit about domains for this as far as what sort of values can we put in for x. And x can get as close to 0 as we like, but of course x could never be 0, because if x was 0, then the height would be undefined. It would be 2,000 divided by 0, so that's kind of a problem. And in fact, x could be as large as we'd like. You can put whatever number you'd like in for x, as big as you'd like, and you'd be able to find a value for h. It's just for really big values of x, you'd have very small values of h. So it looks like there's a lower limit for x. It looks like x can be as small as 0, but couldn't be 0. So starting at 0 but not including it, and no upper limit for how big x can be. So x could be anywhere between 0 and infinity. So for this one, I only have one possible endpoint that I'd have to consider investigating. What happens as we're getting close to 0 for x. I'd also be interested to know what happens at infinity. What happens as x becomes infinitely large? Does that do anything for us? And of course, we also want to know relative extrema as well. What's going on for our cost function for relative extrema inside that interval? So let's get into that. Our cost function as we had it, I had it written as x squared plus 2000x, but you could imagine that as x squared plus 2000x to the negative 1, just to help you take the derivative. First derivative would be 2x, and then for the second term, power would come down. Power would get reduced by 1. So we'd have 2x minus 2000 over x squared. And just so I can have my second derivative handy while I'm here, for the second derivative, it would be 2 plus 4000 x to the minus 3, or in other words, 2 plus 4000 over x cubed. Okay, so we've got our first derivative and our second derivative taken care of. Let's find our critical numbers. For our first derivative, it's not defined when x is 0, and that's fine because 0 is not included as part of our domain anyhow. And we're only going to be interested in the critical numbers that happen, I guess, when the derivative is equal to 0. So let's let our derivative be equal to 0, and let's see what we get. So 2x minus 2000 over x squared is equal to 0. We wind up with x cubed equals to 1000. And of course, that gives you that x is equal to 10. So I do have one critical number, that's 10. And I can check to see what's going on as far as concavity goes at 10. C double prime of 10 is 2 plus 4000 over 10 cubed, which gives me 6. And of course, that's a positive number, which means we are concave up. So I know for sure there's a relative minimum cost at x being 10. So now the question that I have is, number one, what is that cost? And number two, do I get something different closer to the endpoints? Do I get something even smaller? So again, we're looking for absolute extrema, and we've only confirmed that this is a relative extremum. To be absolute, we'd have to know, compared to all the relative extrema and also compared to endpoints, who is the biggest, who is the smallest. So if I were taking a look at this one, I guess first thing that I'd want to know is, what is this relative minimum cost when x is equal to 10? And so I need to know what is the value of my cost function at x equals 10. So let's do that on the next slide. So the cost when x is 10 is 10 square plus 2000 over 10, which is 300. So cost is $300 if our base is 10 by 10. So now the question is, what happens to our cost at the endpoints of our domain? So what happens to the cost function as x goes to 0 for our cost function? And for this, we know what's happening. You know, for x squared, as x goes to 0, that's definitely going to 0. But we know 2,000 over x is going to become infinitely large. Specifically, it's going to become an infinitely large positive number because we're using slightly positive values of x, slightly bigger than 0. This is going to become infinitely large. That's definitely not smaller than 300, so we don't have to worry about having a minimum cost at that endpoint. Also, what happens as x goes to the far right? What happens as x goes to the extreme side of things if we have our base being huge? We know that the 2,000 over x, that term is going to go to 0 as x becomes infinitely large, but also x squared will become infinitely large. So both endpoints diverge to positive infinity. So therefore, we have the absolute minimum cost is $300. And now we can talk about what are the dimensions that give us that $300 box. So the dimensions, we know that x is our base. So base is 10 centimeters by 10 centimeters. And then for the height of our box, this is where we need to go back. And we go back to the original setting things up where we said for this box, the height of it would be 2,000 divided by x squared. We know what x is 10. So for the height of our box, it should be 2,000 divided by 10 squared, which is 20. So now we can go ahead and say the height of our box is 20 centimeters. So when our box is 10 by 10 by 20, we will have an absolute minimum cost of $300. Now for this problem, we've got some sheet metal. Originally it was in a little straight line and then we bent it theta radians up on either end. So we had a 30-meter sheet of metal, and now we've got these two little 10-meter flaps connected to this other 10-meter sheet. And we're going to take that and press it up against a wall so that now that we've got a little trapezoid kind of a shape. And the question is, what kind of bend do we need to do to our sheet metal to get a trapezoid that's got maximum area? As far as the bending goes, we should be able to figure that out right away. So, of course, the smallest amount of bending is no bending. So we know that the minimum we could do for our bend is 0. Of course, I'm not going to include that. I'm not going to say square brackets there because, of course, if you bent it 0 radians, then you wouldn't have any trapezoid to have an area at all. So not much we can do about that. So we can bend it close to 0 radians. And if you're thinking about maximum, well, the maximum would be if we bent it as much as possible and bent the other side as much as possible. They'll actually meet at a point because the 3 segments that are all 10 meters in length, if you bent enough, you'd have an equilateral triangle, all with side lengths of 10. And of course, you know that would mean the internal angle would be 60 degrees. So the external angle, how much of a bend that you did, would have been 120 degrees to get there, or 2 pi over 3. I'm going to say, though, for 2 pi over 3, I'm not going to include that because if you did bend it 2 pi over 3 radians on one side and on the other, then you wouldn't really have a trapezoid anymore. You would have a triangle. So I'm going to say the angle would be somewhere between 0 and 2 pi over 3. Not including 0 because then you wouldn't have a trapezoid, and not including 2 pi over 3, again, because you wouldn't have a trapezoid. I give the formula for the area of a trapezoid there because it's not one of our standard shapes. 1/2 a plus b times h. A is the length of one of the parallel sides and b is the length of the other. And then h is the perpendicular distance between the two parallel sides. So there is a little bit of work that we'll need to do to figure things out. And I'm going to do some of this down below. So if we're drawing things, and I'm thinking about h for just a minute. That's my mystery height that I'm looking for. And of course, that's the same as this distance over here, this height. And I'm doing that because that puts it squarely inside of a nice little right triangle. And right triangle with an angle theta. And we also know that this flap, that's our little 10-meter flap, that's our hypotenuse for that right triangle. We know that cosine of theta, or sorry, sine of theta rather, is h over 10. So our height is 10 times sine theta. As far as the A and the B goes, as I said, A is the length of one of the parallel sides, and one of them measures 10 units, so that one's easy enough to do. If we're thinking about the other one, the one that measures the side B, it's 10 units or 10 meters in the middle, and then we've got a mystery amount and another little mystery amount. The same amount, actually, for both of the two flaps that they add in. I'm going to call this little distance x, and I'll call this one also x. So again, x is the same thing as this distance. That would be the adjacent side on my little right triangle that I've got going on. I know that cosine of theta is equal to adjacent over hypotenuse, x over 10. So x is 10 cosine theta. So that means if we're thinking about what is b, what is the length of my other parallel side, well, I had 10, I have 10 cos theta, I've got another 10 cos theta, so the total length is 10 plus 20 cosine theta. That would be the length of all of B. So now we know all of the missing sides. We know that A is 10. We know B is 10 plus 20 cos theta. And height we know is 10 sine of theta. So now let's put that all together. So we can say that the area is 1/2 A plus B times H. We said that A was 10, B was 10 plus 20 cos theta. And H was 10 sine theta. So if I were to clean this up a little bit, so I would have area being 20 plus 20 cos theta times 1/2 is 10 plus 10 cos theta. And so now we have our area function as a function of theta. It is 100 sine theta plus 100 sine theta cosine theta. Okay. So we're good to go now. We have an area equation. It's a function in terms of one variable. We've already thought about what our domain is, domain from 0 to 2 pi over 3. So let's go ahead and find our derivative and see if we can't find any relative extrema. So let's go for A prime. And away we go. Derivative of sine is cosine. And then I have now a product, so product rule. First thing as it is, derivative of the second, derivative of cosine is negative sine, plus the second thing as it is, derivative of the first. Derivative of 100 sine is 100 cosine. So we get 100 cosine theta, and I've got then plus 100 cosine squared minus 100 sine squared. I'm already thinking ahead that I know I'm going to need to solve for where is this equal to 0. So I already know that when I do that, having sines and cosines squareds all mixed together is going to make things difficult. I know that I can use a Pythagorean identity to get this all in terms of cosines and cosine squareds. So I'm actually going to do that right now before I go further. Sine squared is 1 minus cosine squared. And so if you were now going to clean this up, you would have 100 cosine squared plus another 100 cosine squared. We'll have 100 cosine of theta and then minus 100. Okay, so away we go. Let's start solving and find out what we get. So let's see if a prime is equal to 0. So I'd have 200 cosine squared plus 100 cosine minus 100 equals 0, which of course you could make your life easier right away and divide everybody by 100 so that you'd only have then 2 cosine squared plus cosine minus 1. You could do a little bit of factoring here, so you could do the business of letting u be cosine and u squared being cosine squared, and then eventually you would get it to factor. And if you did that, it would factor as 2 cosine minus 1 cosine plus 1. Okay. So next thing we need to do is figure out what we've got going on here. And I can see a couple of things. Number one, I can see 2 cosine theta minus 1 equals to 0. And that's cosine equals to a half. And if I'm thinking about where is cosine equal to a half, there's a bunch of places where cosine is equal to a half. One of them happens to be in quadrant 1, and that happens to be pi over 3. There would be another one in quadrant 4 as well. Remember that there's 2 quadrants where cosine is positive, but we said our angle would be between 0 and 2 pi over 3, which is between quadrants 1 and 2. So although there is technically another angle out there where cosine is equal to a half, it's not going to be included as part of our discussion. As far as cosine being equal to -1, that's where the cosine of theta plus 1 equals 0. Again, there are solutions for this. We do know where cosine is equal to -1, and that happens to be at pi. But again, that's going to be something outside of our discussion because we said that our domain was going to be from 0 to 2 pi over 3, and pi is outside of that interval, so we don't include that. There's no solutions that are inside of our domain. So I will say no solutions for this one. So when I say no solutions, keep in mind I'm not saying cosine is never equal to -1. I'm saying cosine is not equal to -1 inside of our little restricted domain of 0 to 2 pi over 3. Okay, so I've only got one critical number to look at. There are no places where my derivative is undefined, so the question is, what exactly is it? Is it an absolute max? Or sorry, is it a relative max? Is it a relative min? What's the deal with that? So when I take my second derivative, I'm going to be a little bit cheeky here, and instead of taking the derivative of my first derivative as I originally had it with cosines and sines, I'm actually going to take the derivative of my first derivative after I've already simplified it and wrote it in terms of just cosines. That way I don't have a bunch of extra things to deal with here as far as cleaning things up. So let's do that. Let's find out our second derivative. And so when I do that, so derivative of 200 cosine squared would be 400 cosine. So power came down, power reduced by 1, and then times derivative of the inside, which is negative sine. For 100 cosine, derivative would be minus 100 sine. And then for minus 100, the derivative is 0. So our second derivative is minus 400 sine theta cosine theta, and then minus 100 sine theta. If we ask ourselves what is a double prime of pi over 3. We put in pi over 3 for sine and for cosine. Sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is a half. So we would wind up getting, if we put in the pi over 3 and had our half, root 3 over 2, half, and root 3 over 2, it cleans up to give you negative 150 times root 3, which of course that's a negative number, which means we are concave down, which means we have a relative max at x equals pi over 3. So the question is, what happens at our endpoints? So first off, we need to figure out what is the actual area at pi over 3. And for that, I go back to my original area function that I had. That was that 100 times sine of theta plus 100 sine of theta times cosine of theta. And if I clean that up, again, sine of pi over 3, that's root 3 over 2. Cosine of pi over 3, that is 1/2. And it winds up giving me 75 root of 3. So that's my area at pi over 3. So now the next thing that we need to do is to figure out what is the behavior at the endpoints. So let's add another extra page here and figure out what's happening to our area as theta approaches 0, and also what happens as theta approaches 2 pi over 3. We'll be approaching 0 from the right, and we'll be approaching 2 pi over 3 from the left. And we'll be interested in what happens to our area function to 100 sine theta plus 100 sine theta cos theta. For theta approaching 0, as you approach 0, sine theta approaches 0. So the first term becomes 0. The second term becomes 100 times 0 times 1, which is 0. So the limit is 0. What happens at 2 pi over 3? Well, let's see. For this, I would say, well, as theta approaches 2 pi over 3, I know that sine will be root 3 over 2, and cosine will be negative 1/2. So I'll wind up with, in my first term, 100 times root 3 over 2, and in the second term, 100 times root 3 over 2 times negative 1/2. So in this case, I wind up getting an area that is 25 root of 3. And so we have now 3 options that we saw. We had that our critical number of pi over 3, that we had a relative maximum, and the value we had for that relative maximum was 75 root 3. And at the endpoints, we're either getting an area getting close to 0 or close to 25 root 3, neither of which is bigger. So I can say now the absolute maximum area is 75 root of 3, and that happens when the angle is pi over 3.